We're looking at position, velocity, and acceleration. Alright, we got a problem here. It says a projectile is shot upward from ground level with an initial velocity of 120 meters per second. This is our position function that we're going to be using. And let me just say something here real quick. It says from ground level. So if you can imagine, let's say a cannon, and the actual opening where the projectile comes out of the cannon is going to have to literally be at ground level, okay, for this problem to actually work. Anyway. Alright, well, let's see here. What do we got for some questions? We got what is the velocity of the projectile after 5 and 10 seconds respectively? Now respectively means respectively means 5 first and then 10. I don't know. But we want to find that. Let's see what else we want to find. How long did it take for the projectile to reach its maximum height? Okay, that'll be interesting. And what was the maximum height? So it looks like time here, maximum height. I don't know. Let's just get started. We got some other questions here. I think a total of 6, but let's look at this one here. What is the velocity of the projectile after 5 and 10 seconds? So velocity in the previous problem meant that we need to take the derivative of the position function. Now, the initial velocity is 120 meters per second. Now, remember where that goes, it goes right in here, because v sub naught means initial velocity. But what about this guy? Well, its initial distance, remember, was 0. But anyway, let's just get started. So we're using the position function. And if I take the derivative of the position function, I get the velocity function. So I'm not going to be writing s prime of t here. I'm just going to go ahead and write v of t. Now, the position function, remember, the initial velocity, which was v of naught, is 120, and s of naught was 0 because the distance it got launched was actually from the ground. So, anyway, so that which would be 0, right? Okay, so these are the two guys right here that we're working with. So the question is, what's the velocity of the projectile after 5 and 10 seconds? Well, we just plug 5 into the velocity function, and it gives us it was going 71 miles per second. After 10 seconds, it was going meters per second. This is meters, not miles. 22 meters per second. So it looks like it was speeding up. Now you notice these numbers are positive. That means that it is traveling upward. It says, how long did it take for the projectile to reach its maximum height? Well, that means that when it goes up, it comes back down again as it goes up, right? And then it comes back down again. So it's going to be 0. Its velocity will be 0. Real quick here. I think I said it was speeding up. I don't know what I was thinking. It's actually slowing down. Okay. So how long did it take for the projectile to reach its maximum height? So that means that's when velocity is 0, and we just said 0 equal, and we just solved for t. So it took 12.24 seconds to reach its maximum height. Now that we know how long it took for it to reach its maximum height, we would take t, and the precise number was 600 over 49, plug that into the position function, and of course I'm going to go ahead and approximate at the very end. So it looks like the projectile went 734 feet and 734.69 meters. I got feet on the mind. The next question is, it says, how long did it take for the projectile to hit the ground? So when it came up and then came back down again. Well, that means when the distance was 0. So we set 0, right, s of t equal to 0, and then solve for t. As you can see, when time was 0, the distance was 0. And then, of course, we're going to go ahead and set this other factor here equal to 0. And as you can see, t was equal to whatever that is, which is actually approximated to 24.49 seconds. Now, as you can see, this is how long it took to reach maximum height. Multiply that by 2, and that would be the overall. What's the projectile's velocity upon impact? Just take that number, plug it in. Whoa, doggies, I need to slow it down. Let me just repeat what I just said. So we're looking for the projectile's velocity on impact. Right. So we figured out how long it was going to take for the projectile to hit the ground. Right. That's when the distance is 0. That's the distance between the projectile and the ground. Right. And that distance would be 0. Well, we figured that out, and of course I'm using the exact number here. And we went ahead and just plugged it in, and we end up getting, now remember we get a negative here, which may not make sense for a lot of people, but this tells us that the projectile was falling, right, when it hit the ground. This negative does, at 120 meters per second. So I'm going to try to slow this down a little bit. Okay, last question is, what was the total distance the projectile traveled? Well, remember the projectile started at ground level, it went up, and we figured out what that distance was, that maximum height, remember? And then it came back down again. So this problem has symmetry to it. As you can see, the problem has symmetry to it. So it goes up, and then comes back down again. Well, remember we found the maximum height. And the maximum height happened to be this number here, which I'm using the exact number. And if you just times it by 2, okay, well, you get the overall distance the projectile traveled, which is this number here, right, 1,469.39 meters. Now, we covered about all the possibilities, I think, in this problem that you can possibly cover. I mean, there's some other things, I guess, and it was quite a few calculations, but it wasn't too bad. Now, 15 years down the road, 10 years down the road, or probably even a month down the road or whatever, you have forgotten how to do all of this. Well, if you just can come up with that position function and you know how to plug in V sub naught and S sub naught, all you have to do is go find you a graphing calculator. Now let's look at a graph and graph it. And get out a fairly precise ruler, and we can just look at this graph right here and make these measurements. Now, this is not the projectile flying through here in the air. This is the relationship between the position and time. Okay, I remember when I was first looking at this, because the actual trajectory path is much like this curve actually. If you were to shoot a cannon, you know, but we're not working on that right now. That's later on in calculus. But this curve here represents the position. Okay, and x-axis would be time, and this is position up here. So as you can see here, the maximum height that this thing had reached, which was kind of off the charts here, but you know, you go straight down, and let's see, 10, 11, 12, I don't know, what was it again, 12 point something, and right, so we can actually guesstimate this thing just by looking at a graph, right? Getting a ruler out, doing some measurements, looking at the graph. Now this guy right here, this line, this is the velocity. Now as you can see right here, what's happening is t is increasing, the velocity is decreasing, and then the velocity reaches the t-axis here when the velocity is 0. So at some time, velocity is 0. Now if you go straight up the graph, you can see this is where the maximum was. This is where the velocity was 0. Okay, so the relationship between this line here and then this curve here, right? This represents the velocity, and this represents the position. And then, of course, this over here, what is this? This is where the graph is crossing the x-axis, or I should say the t-axis here. Well, this was when the position was 0 again. So at time 0, and then here, and what was that again, 24 something, right? It was 12, you just doubled it, and we got 24 something, I don't know. But we can, this picture here, you know, you've heard the old saying, picture's worth 1,000 words. Well, just by looking at this picture, we can actually find out a lot of things just by looking at the picture, which is a whole lot faster than doing the calculus, but it's important that we understand the calculus because this is calculus class. All right, well, thank you.